We have an input voltage here, u of t, which for the first part of this problem is a sinusoid, 3 cosine of 6t. We want to find y as t goes to infinity. So we want the response as t goes to infinity for a sinusoidal input. So as t goes to infinity, everything's going to become sinusoidal, and it's going to be easiest to use the frequency domain. So we're going to end up using phasors for voltages and currents and impedances for all of our circuit elements. Now, once we do that, we need a strategy for solving the problem. This circuit is reducible. These two are in series. Those are in parallel with this, which is in series with that 4 ohm resistor. So if we find an equivalent impedance here, seen by the source, ZEQ, then we'll have a circuit that looks like an input voltage phasor U with an equivalent impedance, ZEQ, and this current phasor Y will be U over ZEQ. That current phasor will give us the magnitude and phase of Y of t. So let's take a look at our impedances. Our frequency is 6 radians per second, so omega is equal to 6. So J omega L for this is going to be J2 ohms. This is going to be J1 ohm. And this is going to be minus J2 ohms. So now let's go to a new slide, put in our phasors and our impedances, and do this analysis. So we want to find an equivalent impedance of this whole side here. So as I said, these two are in series, so their impedance is J1 minus J2, which is going to be minus J1 ohms. That's in parallel with the J2 ohm impedance, so that's going to be the product of the two, J2 ohms times minus J1 ohm over J2 minus J1 ohms. That's easy to do in rectangular coordinates. J times negative J is just 1, so this becomes 2 over J. If I move the J into the numerator, that changes its sign, so this is minus J2 ohms. So this 4 ohm resistance is in series with that, so the equivalent impedance, ZEQ, is 4 ohms minus J2 ohms. So now Y is the input phasor U over 4 minus J2 ohms. U is 3 at an angle of 0 degrees because this argument is 6t plus 0 degrees. So 3 at an angle of 0 degrees. If I convert this to polar coordinates, that's 4.47 at an angle of minus 26.6 degrees. So dividing magnitudes and subtracting minus 26 from 0, 3 over 4.47 is about 0.67. This will be at an angle of positive 26.6 degrees. So Y of t is equal to 0.67. Cosine of the frequency is still 6 radians per second times t plus 26.6 degrees. And we're done. Next, we have the same circuit. We want to find y as t goes to infinity if u of t is this step function, 3u0 of t. So this means u of t is 0 for t less than 0 and 3 volts for t greater than 0, and it remains constant forever. So in this problem, we want the response as t goes to infinity for a constant input. So we're back to thinking about the step functions that we saw when we were doing first and second order systems as differential equations. So we're still looking for the particular solution. The particular solution as t goes to infinity is going to have the same form as the forcing function, so our voltages and currents will be constants. For constant voltages and currents, capacitors look like open circuits. They conduct no current, and inductors look like short circuits. So this circuit for a constant input as t goes to infinity looks like a constant voltage, so that becomes 3 volts for t greater than 0. This resistance is 4 ohms. This inductor looks like a short circuit. This inductor looks like a short circuit because everything's constant, and the capacitor looks like an open circuit. And we want the current out of this source, which is going to be y as t goes to infinity. So all of this current just goes through here. This voltage is the same as this voltage. So y as t goes to infinity is just the voltage, 3 volts over 4 ohms, just by Ohm's law. So this is 0.75 amps, and it's a constant.